Okay, so we were discussing about the equipartition theorem, the generalized form of the equipartition theorem. We had already made a statement, and while we attempted to prove the statement, the video had an abrupt end due to some software issues. So let me continue with the proof of the Tolman's equipartition theorem. So just let me once again begin with the proof. Okay, so hope you remember. For any quantum system, let me first begin with the quantum system. For any quantum system, means if energy is quantized, we have the average value of any quantity, say a physical quantity F, is given by average value of the quantity F is given by F is equal to, or expectation value of F is equal to sum over all values, R values, F of R, or F into, okay, you can just say that PR, right? So which we have written as sum over R, F of R, the physical quantity whose average value you have to calculate, times what is PR? You know, PR is equal to e raised to minus beta ER divided by the partition function, canonical partition, that is sum over R, e raised to minus beta ER. So this is the expression that we have to depend if the system has got a quantum nature. But in our topic here, we are going to consider a classical system. So for the classical system, what we have to do is that in order to find out the expectation value of a quantity F by this method, we have to replace the summation in this particular expression, sum over R, has to be replaced with what you call integration. So the summation over the quantum states has to be replaced by integration over the entire phase space which is accessible. So for classical systems, let me write it. For classical systems, you can directly start from here, but I just am writing how it comes. Classical systems, okay, the expectation value of any physical quantity F is given by, you just note the differences, it is given by integral, integral for what? In place of this sum over R, we are replacing with an integration. Integral F into, so there is no quantization, so I need not write FR, okay, F e raised to minus beta H. Now it was sum over R e raised to minus beta ER. Here instead of ER, we are writing the Hamiltonian. Then we have to do the integration over the entire phase space, okay, which is accessible, of course. So divided by, denominator also will be just getting modified. How it will be getting modified? Instead of the summation, we will be having integration. You know, continuous system, summation is replaced by integration, e raised to minus beta H d omega. So this is the definition of what you call the average value or the expectation value of a quantity F for a classical system. Now in place of this F, in order to prove our generalized equipartition theorem, we will be substituting the quantity xi times dou h by dou xj. Okay, so therefore using this concept A, expectation value of xi times dou h by dou xj, this is what we have to find out. That will be equal to, just you have to substitute. So what will be that one? That's equal to integral of that quantity. What's that quantity? That is xi times dou h by dou xj. I told you xi and xj are any of the 6 and phase space coordinates, qi's and pi's, okay, or qj's and pj's, whatever you call. So then multiplied by, so instead of, in place of F, I have substituted this quantity xi dou h by dou xj. then e raised to minus beta h, h is the Hamiltonian of the system, of course, d omega whole divided by integral e raised to minus beta h d omega. So we call this one as our starting equation. You can start right straight away from here, where what is this d omega? You know, d omega is nothing but what? D raised to 3n q d raised to 3n p, means there will be 6n quantities, elemental quantities which are multiplied. Okay, so it's just like dq1, dq2, dq3, like that up to dq3n, and dp1, dp2, dp3, etc. up to dp3n. So there will be 6n quantities which are multiplied. That is a 6n dimensional elemental phase space volume, right? So now you have to evaluate this integral 1. Okay, so just look at the numerator of the integral 1. So that is integral xi dou h by dou xj e raised to minus beta h d omega. We will first of all simplify the numerator, and finally we'll substitute for that one in equation number 1. So in order to simplify the numerator, what I'm going to do, I'm going to introduce a quantity. So you consider, we can just consider the numerator. Okay, so what I'm going to do, I'm going to show that, or just consider this one. Okay, so you consider the partial derivative dou by, I'm taking a partial derivative dou by dou xj of e raised to minus beta h. Okay, randomly I have some motivation, you will understand. So you consider this partial derivative dou by dou xj of e raised to minus beta h. So what will be that one? You know, we have to take the partial derivative of this quantity with respect to xj. What is this xj? Xj is either qj or pj. And where is that qj or pj in this quantity? That is hidden in this h. You know, h is a function of q's and p's. So you have to take the function rule. Okay, so what will be the answer here? So it will be equal to e raised to minus beta h. Okay, so the exponential, the derivative of the exponential is the same thing. Then okay, what is that? Then I have to take the derivative of minus beta h with respect to that one. So that will be equal to into minus, I can say into minus beta, right? Okay, times what? Dou h by dou xj. Dou h by dou xj. So that is by function rule, right? So what does it mean? So from this you can see that, can you write what is this one? Therefore I can write dou h by dou xj into e raised to minus beta h. What will be that one equal to? So these two quantities, so the product of these two quantities, that will be equal to, I have to take that minus 1 by beta to the other side. I can write this is equal to minus 1 by beta times dou by dou xj of e raised to minus beta h. So let me say that this is some equation B which I will be using. Now therefore the numerator of equation number 1 can be modified. So the numerator of equation number 1 can be modified. Let's see what is the numerator of equation number 1. So the numerator of equation number 1 is, you can just have a look at that one, integral xi dou h by dou xj e raised to minus beta h d omega. So out of that, now we have obtained a replacement for this particular term. Okay, so this term will be replaced. So I'm just writing only the numerator of equation number 1. So that is integral xi times dou h by dou xj e raised to minus beta h d omega. This is the numerator. It can be written as, you know, it's with respect to d omega, means it is a 6-dimensional integral. So I'm splitting this integral into multiple integrals. So likewise it goes on. So this is an integral, 6 times it will be there, of course, into, in place of dou h by dou xj e raised to minus beta h, we are substituting minus 1 by beta times. Okay, so I'm writing minus 1 by beta, then we have this xi is already there, this xi has to be retained, so times xi, then what is that? Then you have what is known as dou by dou xj, I'm substituting b here, dou by dou xj of e raised to minus beta h, of e raised to minus beta h. Then okay, of course it is d omega. D omega can be written as d raised to 3n q, d raised to 3n p. Okay, see that I think we have included all the relevant terms here. So let me call this one as equation number 2. So we have 1 and 2. This is the equation. Now so what I'm doing, you have got this particular quantity. You have got see d omega, and this d omega is nothing but this d raised to 3q, d raised to 3nq and d raised to 3np. See, it's just like writing this one. What I'm doing, okay, I can write this one as dq1, dq2, likewise up to what, dq3n, the 3n position coordinates, okay, or generalized coordinates, and then multiplied by dp1, dp2, likewise it goes up to dp3n. So this is the 6n, okay, 6n dimensional, what you can call as what, the phase space volume element, okay, d omega. So what we are going to do is that we are going to take any one of this phase space elements, okay, outside the quantity. So for example, I am taking dq2 outside this quantity. So what I'm going to do, I'm going to rewrite this one. I'm taking let's do it like this, we write it like this, taking dxj, means any one of them. It can be dq1, it can be dq3, or it can be dp1, it can be dp5, okay, anything, all right, one of them. Taking dxj means one particular value of dq, okay, dxj out of d omega, out of d omega. So ഈ ഡി ഒമേഗയുടെ ഉള്ളിൽ നിന്ന്, ഡി ഒമേഗയിൽ ഇത്രയും ടേംസ് ഉണ്ട്, ആ ഡി ഒമേഗയിൽ നിന്ന് ഏതെങ്കിലും ഒരു ക്വാണ്ടിറ്റി, ഏതെങ്കിലും ഒരു എലമെന്റൽ കോർഡിനേറ്റിനെ ഞാൻ പുറത്തേക്ക് എടുക്കുന്നു കരുതുക. സേ ദാറ്റ് ഇസ് dxj is taken outside. Okay, so it is taken outside. Then what remains there? Okay, so the remaining okay, d omega is represented. We are going to represent the remaining d omega as d omega j. Okay, so what is d omega j? D omega j will be equal to the product dq1, dq2, dq3, like etc. up to dp3n, except any one of that variable. Okay, for example, if it was, for example, if in the case of a single particle moving in 3 dimension, it would have been what, see, d omega would be what, dx, dy, dz, dpx, dpy, dpz. This is what you know for a single particle. So what I'm doing, for example, I'm taking dz out of that. So how do we write it? We'll write dz into, now all other remaining 5 terms will be written as d omega z, for example. Okay, so d omega z is the product of all other terms except dz. So we can say dz into d omega z will be giving you back d omega. Likewise, we are taking say that dxj is taken outside. You will understand why, what's the benefit of that. Okay, it's in order to do one integration simple, right? So taking dxj out of d omega, the remaining d omega is represented by d omega j, such that always remember, such that dxj into d omega j will give you back that entire d omega. Okay, so therefore let's see what's equation number 2 becoming. Therefore equation number 2 can be modified as, equation number 2 I'm writing integral xi into dou h by dou xj, right? Dou h by dou xj times e raised to minus beta h d omega, that can be written as, okay, that can be written as multiple integral. So I'm writing multiple integral. Then what is that? Minus 1 by beta into xi. See, up to here we have written Now see, out of this one we are going to just rewrite this one. So then let me use a bracket to understand that I'm doing dou by dou xj of e raised to minus beta h. Then this is d omega. I'm splitting it into two terms as I have discussed here. So times dxj into d omega j. So this is what I have followed, right? So let me call this equation as equation number 3 for the time being. Now just what we have done is just we have done a splitting, that's all. Okay, nothing else. So let me use a bracket here. So yeah, here I can use a bracket, right? So that's this expression. Let's see what to do here now. Next, so now what I'm going to do is that I'm going to evaluate this quantity. I'm going to evaluate this particular quantity up to here. So you know that one of the this is actually how many integrals will be there? There will be 6 integrals here. Okay, so first integral may be on dq1, second integral is over dq2, likewise the last integral will be over dp3n, right? So these are all 6 integrals are there. So out of that, one integral is with respect to dxj, right? So that integral I'm going to perform, okay, and remaining integral will be there, right? So remember, so here remember one thing here, xi by xi we mean what? Either qi or pi. I can say qi or pi. Then xj can mean what? Some other value, qj or pj, any value, it can be anything. And you know, d omega j, it means what? dq1, dq2, likewise up to dq3n. Okay, again multiply by dp1, dp2, likewise up to dp3n. But one of these terms will be missing, okay, except so whichever term dxj we have taken out, that will be missing, except dxj, okay, which can be either dqj or dpj, can be a dqj or dpj, that has been taken out. Okay, so as it has already been separated out of, it's understood, okay, only for understanding I'm writing it out of d omega. d omega il already ഏതെങ്കിലും ഒരാളെ പുറത്തേക്ക് എടുത്തിട്ടുണ്ടാവും, അതൊഴിച്ച് ബാക്കിയുള്ള എല്ലാം കൂടിയാണ് d omega j എന്ന് ഞാൻ okay, as I have just explained here. So that is what we have done here. Now let's continue with, okay, it's quite simple. Now whatever we have written here as what I have just marked here, we can do it by integration by parts. Okay, so can you see that? What is that? It is xi times dou by dou xj of e raised to minus beta h dxj. Okay, so I'm doing it by integrating by parts. So integrating the selected term, we can say, right, like that, integrating the underlined term or selected term. This is only for us to understand by parts. So out of 6 integrals, we are performing one integral inside, right? Parts, integrating by parts. I'm writing it. What is that integral? I'm separating out. It is integral xi times dou by dou xj of e raised to minus beta h, okay, dxj. So integration is done with respect to xj. What will be that one? So you can just do this one integral by parts. So this is first function, this is second function, u v dv, okay, like that. So you can see that. So that will be equal to okay, what is that? First function into, that is xi, into integral of the second function. What is the integral of the second function? It is integral with respect to xj. So this is dxj. So integral of the second function will be e raised to minus beta h itself, right? Okay, exponential function. So e raised to minus beta h, and I have to apply the limits the limits of this function, of course, that will be the values of xj. Okay, limiting values of xj. So let me write xj, some xj1 to some xj2, xj1 to xj2, or xj to xj dash, whatever it is. Okay, so minus, so I have performed the first one, minus integral of derivative of the first function. So what is derivative? Derivative of the first function means derivative of first function is xi with respect to which one? With respect to xj, right? So dou xi by dou xj, derivative of the first function, into integral of the second, means e raised to minus beta h, and we have to complete the integration with respect to what? Xj itself. So this is exactly what we are going to get, right? Now have a look at this expression. We will be able to, on a close observation, we will be able to see that this particular thing will be giving you 0. It will get vanished. This first term will get vanished. Why it gets vanished? Because you know it is e raised to minus beta h. So a little thought over that. E raised to minus beta h, and this h is a function of q's and p's, right? So, and what is this xj1 and xj2? xj1 and xj2 are the two extreme values of either q or p. Okay, so extreme values means okay, it's either the position value or the momentum value. So extreme values means it can take up some infinitely large values. So whenever either xj1 or xj2, okay, or we can say q's or p's, take extreme values, means either q or p becomes infinite. Okay, what will happen? The Hamiltonian will become what? Infinite. So when q or p tends to infinity, means extreme values, theoretically, okay, the momentum value can go from minus infinity to plus infinity. Position can also get go from minus infinity to plus infinity theoretically. So whenever it happens, what will happen? That the Hamiltonian, which is a function of these two variables, will be tending to what? Infinity, right? And so what will happen to the term e raised to minus beta h? So e raised to minus beta h is 1 by e raised to beta h. So when this h tends to infinity, it will be 1 by e raised to infinity, which tends to what? 0. So the first term vanishes in the case of extremum values of q's and p's. So only the second term will remain. And what is the second term? The first of second term, can you say it is dou xi by dou xj? So it will be giving you only one thing. What is that? So that will be giving you only, we can say that one integral. So that is equal to minus integral. So this is 0 minus integral. Dou xi by dou xj will be delta ij, which is Kronecker delta ij. That will be equal to non-zero 1. It's equal to 1 only when xi equal to xj. And for all other values, that will be equal to 0. So that is delta ij e raised to minus beta h. I am retaining all other things as such, dxj. So this is what we are going to get. Okay, so let me call this one by some number. Yes, that is equation number 3 or equation number. So let me say that this is some equation number 4. That is side work, right? Now, therefore, substituting back, equation number 3 will be modified as how do we get equation number 3 modified? That is equation number 3 was xi, okay, dou h by dou xj times e raised to minus beta h d omega. This d omega we split it. That will be equal to some multiple integral, okay, multiple integral minus 1 by beta. You can check it, okay, minus 1 by beta. Then whatever we had integrated, that I'm just putting it back, that is minus delta ij. I'm putting back equation number 4, e raised to minus beta h dxj has again come back. Then what was remaining? D omega j. Everything except dxj was considered as d omega j. Okay, d omega j. Now see the interesting thing. What's the interesting thing? You can see, can't you see that this dxj into d omega j becomes what? Once again it becomes back to d omega, right? The product of dxj with d omega j is once again d omega, and the integration has got back once again, right? So what happens here is that this one becomes equal to, so I can write this one simply as, I can just forget about all these multiple things. It's represented by a single integral. So that is equal to 1 by beta. There is two negative signs, that becomes positive. 1 by beta times delta ij Okay, all this can be taken outside. Then integral, remember this is 6th dimension integral. Once again I am representing as a single integral. What is happening? E raised to minus beta h, okay, d omega, e raised to minus beta h d omega. So this thing and these two things put together we are writing as the integral, and these two terms have been taken outside, right? So let me say that this is my equation number 5. So that is the numerator. That was the numerator of our expression. That was the numerator of our expression, right? Okay, see, okay, like, see where it was. Yes. Okay, it was this expression. Okay, no to mention about the numerator. So this one was our expression, right? Okay, here, yeah, numerator of equation number 1. That is what we have evaluated just now. Now you note that what is the denominator? What is there in the denominator of equation number 1? That is integral e raised to minus beta h d omega. So let me just go back. So I'm substituting in equation number 1. Therefore, equation number 1 becomes, what is equation number 1? On the left side we had xi dou h by dou xj. This is what we are trying to evaluate. Okay, so that is equal to numerator is obtained as 1 by beta delta ij times integral e raised to minus beta h d omega divided by okay, what was the denominator? Denominator was just simply e raised to minus beta h d omega. Now you can see that these two terms are one and the same, they will get cancelled out. So what is remaining there? It is nothing but 1 by beta, see that this is beta delta ij. And what is beta? Beta is inverse temperature, beta is equal to 1 by kT. So that will be equal to 1 by kT times delta ij, which is nothing but what? That is nothing but equal to delta ij times kBt, and is not what we need. Of course, that was our, okay, what you call the general mathematical statement of the general, or what you call Tolman's equipartition theorem, which is the expectation value of the product of xi with dou h by dou xj is equal to delta ij kBt, where T is the temperature of the system. Okay, so this is the proof of our generalized equipartition theorem. Before we end up this discussion, a word why it is known as generalized equipartition theorem, because this theorem does not take into account the exact or the precise form of the function h. Okay, so ഇവിടെ h of qp എന്ന് മാത്രമേ പറഞ്ഞിട്ടുള്ളൂ. So in this expression h, the form of h is not precise. The exact, okay, form of Hamiltonian is not precisely defined. So it is not okay, precisely defined what kind of a function h, whether it is a quadratic function or it is any other type of function, or because h can be, the Hamiltonian can be a function, right, of q's and p's. It's not clearly mentioned, or it is not generally mentioned what kind of a function is that. So due to this reason, it is known as generalized equipartition theorem, because it is applicable in general form of the Hamiltonian, which is not okay, precisely defined. So that is the general form. And next we will discuss about the Boltzmann's equipartition theorem, where the Hamiltonian is expressed as a quadratic function of coordinates and momenta. So that is a special case. Okay, we'll see that. Now before we conclude the session, let's have two very important results which we get from that expression. So special cases. So it's a very simple, very short. I'll be taking maybe some 2 to 3 minutes. So let's assume let xi is taken to be equal to xj, and as I told you, this xi and xj can be any one of the 6 and phase space coordinates. So let's say that this is equal to pi. So in that case, what will happen to our generalized equipartition theorem, that is in place of xi I'm just writing pi times dou h by dou pi, right? Okay, dou h by dou xj will become dou h by dou pi. So what will be that one? That is the expectation value of pi. What is dou h by dou pi? You know, dou h by dou pi will be equal to qi dot, is not, by Hamilton's canonical equation of motion. You know, the Hamilton's canonical equation of motion says that Qi dot is equal to dou H by dou Pi, and Pi dot is equal to minus dou H by dou Qi. These are our very familiar Hamilton's canonical equation of motion, which governs the motion of phase space points, okay, or representative points in the phase space. So that is always applicable. So this is one thing. And right side is delta Ij into Kt. You know, delta Ij is equal to 1 because I have taken both I and j equal to what? I itself. So delta Ij will be equal to 1 here. So I can say that this is equal to simply Kt. So let me call this one some equation number, say 7, whatever it is. Okay. Some continuous number you can give. Now similarly, when xi is equal to xj, these are some special cases, is equal to say qi, some values of coordinate. So what will be this one? So that becomes qi times dou h by dou qi. LHS of the equipartition generalized equation theorem will give you this one. That is equal to qi times, what is dou h by dou qi? Dou h by dou qi will be equal to minus pi dot. So what I have to do is that I have to write into minus pi dot. So that will be equal to, I can say once again, the right side is what? Kt itself. Okay, so this is what we are going to get. So pi qi dot is equal to expectation value of pi qi dot equal to Kt, and the negative of the expectation value of qi pi dot is also equal to what? Kt. So these are two important results that we are getting. Okay, now you know that our system is having 3n degrees of freedom. So if you add all these terms together, equation 7 and 8, if you sum it over, so therefore summing over I is equal to 1 to 3n. Okay, what will be equation number 7 becomes? So if you take summation over all terms, so each term will be, each I will be contributing Kt. So if there are 3n terms, then what will be the total contribution? Total contribution will be 3n Kt, right? So it will be 3n such term. So I can write expectation value of sum over I, I'm summing it over first, pi qi dot, okay, sum over I pi, okay, yeah, I can write like that also. So that is sum over I pi qi dot, which is equal to, what is that? Expectation value of sum over I pi into, what is qi dot? That is dou h by dou pi. Okay, dou h by dou pi. So that's equal to, when you do that, I equal to 1 to 3n, there will be 3n kt terms. So that will be total 3n kt. Okay, so I think you are coming close to something like, is not? So there is some smell of very important result in the nearby future that we will be doing in the other discussion next lecture. So similarly, equation number 8 can be modified by taking summation over. So sum over I, expectation by sum over I 1 to 3n. Okay, what is that? See, qi times dou h by dou qi is equal to minus of expectation value of sum over I qi into pi dot, right? Q and pi dot, that is also equal to what? 3n kbt. So that is my question number 10 to save it. So we will use these two results later in the application of equipartition theorem, or also in the proof of the Boltzmann's form of the equipartition theorem. We will be using these two results. So remember, before we end up, the general equipartition theorem is stated mathematically, and mathematical statement, I think by the time you are familiar with the meaning of the terms also, this is the mathematical statement of the generalized or Tolman's equipartition theorem. Okay, thank you.